So I'm going to talk about new results in two new, actually, general probabilistic characterizations of quantum theory, and I may talk a bit about what is the significance of the GPT program for quantum physics. So the basic plan of the talk is, okay, so this goes, where does this go?
Like around your head? No, the other way around. I think. So, okay, maybe more practical.
Yeah. Okay. Right, so the general probabilistic framework, sometimes called the operational framework, allows one to describe quantum theory in terms of its state space, its mixed state space, measurements as POVMs, composite systems, potential dynamical evolutions, and a very broad framework for describing systems in terms of probabilities for processes. So I'm going to briefly discuss the physical interpretation of the GPT framework and potential...
Could you lift your hair?
Sure.
Yes.
Potential physical significance of results in it. And then I'll summarize the relevant mathematical content of the framework. And now a major aspect of the program, although it's not the only thing one does with it, is to formulate principles that might be mathematically appealing or of physical significance, or maybe they describe properties of information in the theory. That can be used to characterize mathematically quantum theory in the above sense of density matrices, POVMs, CP maps, and so forth, within this framework. And some say, some call this reconstructing quantum theory. Okay, and often these characterizations go by way of characterizing a class of Euclidean Jordan algebras. And this is already very close to quantum theory because, as Jordan, von Neumann, and Wigner showed, this is complex, real quaternionic, and 2- and 3-dimensional octonionic quantum systems, plus any system whose set of normalized states is a ball in whatever dimension. And we're going to restrict everything to finite dimension for this talk, unless I mention otherwise. Makes things easier to see the conceptual content frequently. And often, although not always, there's nothing essentially new for these topics in going to infinite dimension. So the two new characterizations I'm going to talk about are a class of Euclidean Jordan algebras from abstract spectrality, a convex abstraction of the decomposition of density matrices into their eigenbasis, and strong symmetry. And this abstracts properties of taking density matrices to unitary transformations of density matrices. And that's with Joachim Hilgert from the University of Paderborn. I'm also, the second characterization, which is not yet published, is uses homogeneity of the cone of unnormalized states and transitivity of the connected symmetry group. How far am I into the talk? I'm going to set a timer. 5, okay, thanks. Right, and once we've gotten to Euclidean Jordan algebras, there are various options for getting to standard quantum theory, that is complex quantum theory, among the Jordan algebraic ones. And I'll mention energy observability, local tomography. The cubist group of Chris Fuchs et al. Likes to think the existence of POVMs, symmetric informationally complete POVMs, is another one. We know, in fact, they don't exist in all real dimensions, for instance. Okay, so we might want to reflect a bit on whether such results are really important for quantum foundations. And that, to me, means understanding how quantum physics works as a theory of the world. In other words, interpreting quantum mechanics. And we might want to do this in order to resolve apparent paradoxes in its formulation, or to combine our understanding of quantum aspects of the world with gravitational and space-time physics. In any case, we really want to understand how our physical theories work and how they relate to the world. That's arguably even part of having a theory. And so another thing that the GPT framework can do is connect the possibility or impossibility of certain physical phenomena that might be thermodynamic or information processing protocols, cryptography, for instance, of various types, bit commitment, possible or not, with geometric properties of the spaces of states, measurements, and dynamics. And so even if we don't think it's going to be a framework for new physics or extensions of quantum theory, and perhaps it could, it still tells us a lot about the nature of quantum theory, and that might be helpful in applications, or indeed in combining things with gravity. All right, I think, so let's think a little bit more about this. We might wonder, do some principles that we can use to characterize quantum theory fit better within some interpretations than others? For example, are some make more sense in a many worlds view, others perhaps in a personalist or decision theoretic view or cubist type view? It seems like perhaps we end up with GPT characterizations of quantum mechanics that you might argue support one and also the other. I mean, the Pavia group has characterized things in a way that you might say the church of the larger Hilbert space, the ability to have that is the key aspect, and maybe a many worlder would like that. On the other hand, the whole framework is about probabilities of observations, and that already seems like perhaps we're even biasing things towards the decision theoretic personalist probability view. All right, a few more remarks on the significance of things. It's important to think about meaty quantum physics, where we have specific free Hamiltonians, interacting particles, distinguished observables that are physically significant, like position, momentum, and spin, that have some relation to space-time, even if you're not doing a full space-time general relativistic picture of things. Versus a quantum information theoretic view where we might idealize things and assume we can perform all CP maps, measure all POVMs, prepare all states, and we're not thinking about computational and perhaps physical limitations. And this is, for example, often useful in a computer science point of view on cryptography, especially if you want to prove no-go theorems. If you assume you can't do it with any of these things, then of course you can't do it with the physically possible ones. But nevertheless, I think it's important to think about, when we're thinking about principles, are they most natural in this information theoretic setup, or in a setup where we maybe view the POVMs and the density matrix formalism as an arena for more meaty physics, but we don't necessarily think that we can get to all parts of this arena. In fact, one message of quantum computation is sort of that Hilbert space is a really big place, and we can get to maybe more of it than people perhaps might have thought it was easy to get to, but that's still an exponentially small fraction that we can efficiently at least explore. And that business of the fact that we can't efficiently explore all of Hilbert space actually seems to be important in some of the quantum space-time GR programs to combine them, like the id from bit stuff that's, for example, Susskind and the black hole folks that Renato was talking about yesterday. Often complexity of doing an operation is actually related to the space-time length of something like a wormhole. So, this idea that we need to take into account computational limitations, and that this sort of GPT as a monoidal category where you can do all the processes is maybe more of an aspirational thing that we're trying to realize when we try to do quantum computing, or try to approximate, rather than really operational. Okay, and finally, the framework is a source of compelling and interesting mathematical questions about convex sets and their geometry. And I think that's valuable whether or not it contributes to foundations, but I'm not really going to emphasize that here because this is, we're mostly interested in quantum foundations here. Okay, so quickly summarizing the framework. We've got a compact convex set, I usually call it omega, and it's in some affine space of dimension n, right? Affine space is just like the Euclidean model of space. It's it's like a vector space, but there's no preferred zero. It's a natural place for talking about convex sets. And let me just see if I had, yes, I did have a, so I'll just give you a picture of some examples in a two-dimensional affine space. This is a rebit, or the bit of a real quantum system over the reals. It's just a disk. A classical bit is just a straight line. Classical three-state system is a filled-in triangle. And if you have one side of a PR box, your state space is a square, again, filled in. Just to have some little bit of a picture. Okay, so we say a state is pure if it's extremal in the convex set. So we can't write it as a non-trivial combination of other states. And we take affine maps to be candidate dynamical evolutions. And why affine maps? Because they commute with convex combination. And pretty soon we'll linearize all these things. We'll add one more dimension. These affine stuff will become linear. And that means if we flip a coin to decide how to prepare something, then we do a process. We want the outcome, to be the same whether we know the outcome of the coin or not. Basically, we could calculate based on knowing each outcome, and then take the convex combination, or take the convex combination first and plug the mixed state into our dynamics. Should get the same answer. Very operationally reasonable. Okay, concepts we'll use are the automorphism group of this state space, sometimes called symmetries. These are candidate reversible dynamics, right? Rho goes to U rho U dagger in quantum theory, and the transpose is actually also an automorphism, although we rule it out for other reasons. So we have a group of affine maps that preserve the state space. They don't take it into itself, they take it onto itself, and those are the symmetries. The reversible transformations. Okay, I don't really think we need to know too much about the centroid, but it does fix, the automorphism group fixes the center of gravity of the convex set. Well, okay, let me just say this. And we can, if we want, then make this affine space into a vector space by taking the centroid as 0, introduce an inner product such that the automorphisms are all orthogonal transformations. Because that is actually often very useful. Okay, I'll talk about measurement probabilities. They're given by effects, which are affine functionals whose values are probabilities. And a measurement is a list of effects that add up to the unit effect. This is the effect that takes the value 1 on everything in omega, and in fact on the whole affine space, the constant functional. That's just so the probabilities of a measurement add up to 1, no matter what state you put in. Okay, and actually that was slightly redundant with this slide. Okay, if we give the convex compact set of effects the pointwise ordering, so we say one thing is bigger than another if it has bigger values on everything in the convex set, then S is the interval between 0 and the unit, which is this constant functional, in that ordered linear space. And quantum mechanically, what are these effects? They're just the functionals. Rho goes to trace E rho, where E is a POVM element. And what is this interval? It's the set of E between 0 and 1. Okay, and then you have to trace with it. And this U is just the trace, in fact. So trace of I times something is just its trace. So any questions about that formalism? I mean, it's important just to get a flavor that this is just a generalization of what we do in quantum information theory. Okay, we usually linearize, so we add a dimension, and we make this normalized state space the base of a regular cone, right? Base just means we take 0, and we take all the rays through this flat set, and that gives you the cone. It's a slice through the cone, if you like. All right, a cone, well, here's the formal definition of cone. I don't think it really matters too much. And so we extend the representation of this automorphism group acting on the Euclidean space where the normalized states live to the whole place, to the whole space, and it can still be a subgroup of an orthogonal group. So now we have this positive cone. We can make the vector space ordered by saying x is bigger than y if there are differences in the positive cone, and extend our effects to linear functionals. And this is possibly the most common setting you'll see. And then these effects generate the dual cone. They're the functionals that are non-negative on everything in the primal cone. Okay, why should we bother linearizing? Well, basically, it's to represent dynamics conditional on observations. So we say a map is positive if it preserves the positive cone. Takes, this is the definition of positive map in quantum theory. In fact, preserves positive semi-definite matrices. And then a candidate probabilistic dynamics, so one it may not occur with probability 1, is one whose adjoint acting on the dual space takes the effects into the effects. Because we don't, you can have positive maps that blow up your probabilities bigger than 1, that would be bad. But we can handle it. And of course, I don't know if I said, actually I probably should have said, all right, it doesn't seem to appear on this slide. This curly E represents some subset of the full set of possible effects. We call a theory unrestricted if this E, which we interpret as the effects that we allow in our theory, is all of the, this whole order interval, all of the mathematically reasonable effects. But there are interesting theories where we don't allow all measurements. And so that's what this E is. It might describe some subset. For example, we might take a subcone of the dual cone and say only the effects that are between the constant functional and 0 in that subcone are allowed, or there are other things you can do. Interesting recent work on that, actually. Okay, and if the system is unrestricted, all you have to do to say it preserves effects is just say tau star applied to U is U. Trace preserving, it's the analog of trace preserving quantum maps. Okay. So we say a cone is reducible if you can split the vector space into 2 parts, and every extreme ray, and this is just multiples of the extreme pure states, multiples of pure states are an extreme ray, is in one of these spaces or the other. And these are non-intersecting spaces. And that's just saying that their system decomposes into 2 parts whose relation is classical. There's no coherence between them. Every state is a convex combination of a state in one space and a state in the other. So classical theory, a classical n-state theory, is just the direct sum of n one-dimensional vector spaces with their only reasonable ordering. And the base of this cone, of course, is just the probability simplex. So that's omega in the classical case. And so every finite dimensional cone can decompose uniquely into irreducible cones, which have no further decomposition. And so we call these irreducible, I believe, that's the word I like to use. And generally, you can understand the behavior of an arbitrary cone in terms of the behavior of its irreducible components. Okay, so concepts we're going to use in the first characterization: perfectly distinguishable states and frames. So we have states omega 1 through omega n. We say they're perfectly distinguishable if we have a measurement, E1 through En, such that Ei of omega j is delta ij. So if we know you prepared one of these states, if I get a certain answer, I know which state you prepared. It could be a submeasurement. It doesn't really matter. Okay, we call this a frame or an n frame if we want to emphasize how many states it has. It's maximal if you can't make it a subsequence of any other. You can't add states that are still distinguishable, pure states. And order matters here. Different orders are different frames. And of course, if we do restrict the theory, we might end up with less distinguishability than if we allow all effects. So the set of frames depends only on omega and on both omega and E, but in this case, where we take an unrestricted theory, it only depends on the state space. Okay, so here is the first result, and I'll define the terms on subsequent slides. Any finite dimensional complex convex set that is first spectral and second strongly symmetric is the space of normalized states of a simple Euclidean Jordan algebra, or it could be a simplex, in other words, classical. Here's the reference. I do urge people to look up both versions depending how much background you want. The published version has a kind of a better discussion of the theorem and implications. Yes? That will come on the next slide. Yeah. You can, this may be paywalled, so you can look at, there's a preprint on my blog, which is this thing, Wine, Physics, and Song. So those are all big things in Vienna, so you ought to be able to remember it. Okay, spectrality says that for each normalized state, there is a frame, and remember these are pure states, the frame, such that omega is in its convex whole. So it's just a convex sum of distinguishable states. And this is kind of, you could think of this as classicality, I guess. Not classicality of the whole state space, but saying each state in the theory belongs to some classical subtheory, some simplex of perfectly distinguishable states. And then strong symmetry says for each integer r, the symmetry group, odd omega, acts transitively on the set of R frames of size R. And what does acts transitively mean? It means you take any two of these things, there is something in the group that takes the first one to the second one. That's transitivity on a set. So, and of course we have to say R frames because it's not necessarily going to take an R frame to some frame of a different size. And in fact, you can let R be the ambient dimension plus 1, and that's good enough. You don't have to stipulate it for any larger integers. Okay, so as I mentioned, we've abstracted the spectral theorem for density matrices, and strong symmetry abstracts the fact that for two orthonormal lists of rank 1 projectors, with index, let's say from 1 to m, there's a unitary that takes the ith projector in one set to the ith projector in the second set. It's just that we can take any orthonormal basis to any other orthonormal basis in quantum theory. But it's an abstract convex statement of that. So any questions about those properties? Okay, let's check the time. Okay, so with Markus Müller and Cosmin Ududek, we had already observed the converse, which is fairly easy using known mathematics about Jordan algebras. And we'd also characterized this same set of state spaces, but with one additional assumption, and that was no higher order interference in the sense of Raphael Sorkin, and we heard quite a few talks yesterday, or at least a couple, in which the notion was used, and experimental tests of whether in fact one can see it or not were described. So one might have hoped, and I will admit I had kind of hoped, to explore a landscape of theories with these beautiful properties, strong symmetry and spectrality, plus higher order interference, but they don't exist. That's the burden of our the theorem with Joachim. I'll also remark that many quantum phenomena, like the measurement of majorization of measurement probabilities by the spectrum, which is what happens if you measure these perfectly distinguishable states, the measurement that distinguishes them. And this was shown by me and Markus Krum and Marius Krum and Markus Müller. And then Kiribella and Scandolo had a I think they basically also, they have a theorem about majorization. Let me not say that, they didn't start precisely from these, but I think their assumptions we could show ended up implying them. So I think that implication was actually some work with Karen Lee and John Selby. Also, people derived, Karen and John had derived Grover-like bounds on query complexity using strong symmetry and spectrality, or in fact, some sets of principles, but that turned out to imply it. And And we can see that these are Jordan algebraic settings. So it's not that far from quantum theory that these results live in. So in a way, it's sort of disappointing if we'd hoped to do a lot of nice physics and information processing that's like we do in quantum theory, but in these zany theories with higher order interference, it's not going to happen. And to some extent, that's a lesson that's coming out of the GPT framework, is that it doesn't take too much to characterize things that are very close to quantum theory. And when you think of the nice properties of quantum theory, put a few of them together, and often you will get there, or get very close, because you'll get to these Jordan algebras. I don't think we really need to describe the Jordan algebras themselves. It's just an abstraction of symmetrized multiplication of Hermitian matrices. You symmetrize to make them still Hermitian. So it's an algebra on quantum observables. Jordan invented it for that reason. Jordan, von Neumann, and Wigner showed that, classified it in the way I've already described. So now, if there are any, I guess I'll pause for questions on that first characterization, and if not, I'll start on the second one. All right, so the second characterization involves homogeneity of this cone of unnormalized states and continuously reversible pure state transitivity. And let me remind you that the interest in these, so first I'll just define it. An order automorphism is a positive map, tau, such that tau of V plus is not only a subset of V plus, but in fact is equal to V plus, the positive cone. So it preserves the, and positive includes linear. So it preserves the convex structure of the cone. In the quantum case, the connected identity component of this group is just X goes to AX A dagger, where the Krauss operator A is non-singular, and there's only one Krauss operator. Those are the automorphisms of the quantum cone. And the full automorphism group is generated by these pure Krauss operations with a non-singular operator and any transpose. And again, we rule out the transpose in quantum information theory because of positivity conditions for entangled states. So the automorphism group is a compact the automorphism group of the normalized states is a compact subgroup of this automorphism group of the cone. And again, why would we care about the automorphism group of the cone? That seems like a pretty abstract thing. It doesn't even preserve the normalized states. But if we take an automorphism and we shrink it by an appropriate positive real scalar, we can always make it normalization non-increasing. So it can represent a special kind of dynamics conditional on a measurement result. So that's a reason we might be interested. Let me just mention the spin factor case. The state space is a ball of whatever dimension. The cone is a Lorentz cone, or ice cream cone, people sometimes call it. It includes the qubit, the rebit, the quaternionic and octonionic bits are spin factors. And the automorphism group is generated by Lorentz boosts. Of course, uniform dilation and shrinking, reflections, and rotations. So I think that's called the orthochronous Poincaré group in relativity. Orthochronous because you can't use negative factors here. So the direction of time is preserved. And so in general, the ball base is going to go to some ellipsoidal base for the cone. But affine, that's basically the same structure. They're related by an affine map. Okay, and the automorphism group is generated by, of the normalized states, is generated by rotations and reflections. So we say a GPT is homogeneous if it is unrestricted, and its cone of unnormalized states is called homogeneous. Well, sorry, okay, this is redundant, but we call its cone homogeneous if the automorphism group acts transitively on the interior of the cone. So some people call these states of maximal information. They won't give you zero on any measurement outcome. Okay, and I guess we'll call the GPT homogeneous if its cone is homogeneous, obviously. An example, just to show you that there are examples that are not quantum mechanical. Yeah, I'll just say, since I had a slide about the kosher-Vinberg theorem, but yes. Yeah. Excuse me?
Homogeneity, like a physical meaning, is that that there is a channel that maps state to state for every pair of states.
So for every pair of internal states, so states of maximal information, I think the Pavia group likes to call them, there is an automorphism, not just a dynamics, but an automorphism that takes one to the other. So that's a very special kind of dynamics that preserves a lot more coherence than a general positive map. So that's
kind of strong assumption. Right?
Yeah, it is a strong assumption. So I'll mention the kosher-Vinberg theorem, which I had a slide about, but then the last version of the talk got corrupted, so I had to emergency replace it with a backup. Glad I made a backup. In about 58, kosher, and around 1960, Vinberg showed independently that a homogeneous cone that is self-dual is the cone of a Euclidean Jordan algebra. And what does self-dual mean? Well, we like to call cones weakly self-dual if it's affinely isomorphic to its dual cone. So you take a linear map of the space onto the dual space, and you can find a linear map such that the cone goes onto the dual cone. That means they're isomorphic as convex sets. Self-duality without the weak qualifier is a little bit more. So when we take a isomorphism of the space onto the dual space, which you can always do in finite dimension, that determines a bilinear form on the primal space, namely, take an element, if you want to do x and y, take y, the bilinear form on x and y is take y, put it into the dual space with this isomorphism. Now you can evaluate it because it's a functional on the primal space, and you get a number, and that's a bilinear form. It's non-degenerate because this is a linear isomorphism. The spaces are the same dimension. And if it has the property that b of xx is always non-negative, then that bilinear form is an inner product. But that's not always the case. And there are cones, like this cone with the square base that you get on one side of a PR box, that are weakly self-dual, but you cannot choose this isomorphism so the bilinear form is an inner product. And as a side remark, it's common also to formulate GPTs all in the primal space and just use an inner product to represent duality. Yes, Andrew.
Yeah, with this one half of the PR box, is the intuition for this that the dual of a square is like a diamond, which kind of looks like a square,
yes,
but doesn't have this.
It's 45-degree rotated.
But
you cannot.
But it fails on this inner product.
Yeah, you can't cook up an inner product that will make it coincide. Yeah, that's square is often a great example for weird stuff. Thank you. Right. So I'll just mention, just so we have an example, the smallest non-self-dual example. So the reason I mentioned kosher-Vinberg is that we want to talk about other things. We don't just want to have EJAs. So we take the symmetric matrices, but we take the subspace where these two are zero. The symmetric real matrices, the subspace where these two matrix elements are zero. You can define the Vinberg cone by these constraints, but these are just telling you that two submatrices are positive semi-definite. That's a determinant condition. So basically, we're just taking two positive semi-definite cones and stapling them together at one diagonal matrix element by saying it has to be the same in both of these. And there's a recursive stapling construction that you can make all homogeneous cones from, but it's not always as simple as putting zeros in a symmetric matrix. Okay. So there are non-self-dual examples. Hideyuki Ishii gave non-self-dual but weakly self-dual examples, which is also interesting. The dual of this cone is just the PSD matrices in this space, positive semi-definite matrices in this space. So this is actually bigger because we haven't put on the third constraint that would be full determinant. Okay. For a little more intuition about homogeneity, here's the quantum case. You want to take x and y, which are full rank. You want to take x to y. You just apply this map. You turn x into the identity with this Krauss operator, and then you turn that into y with that Krauss operator. Okay. Now we're going to say a GPT state space, that should say, has continuously reversible pure state transitivity if the connected identity component of the symmetry group of the normalized states acts transitively on the pure states. It's a common assumption. I'll just state the theorem. Was there a question? Or okay. So this is from joint work with Kozmin Ududek, and it's still in preparation. The final, there's other results in this paper too. Homogeneity and continuously reversible transitivity imply that the system is an irreducible Jordan algebraic system. It's irreducible because if it had these different sectors that are classically related, that had different structures, well, different structures or not, you can't continuously go from one of these sectors to another because we said there are no pure states that are in between. So we don't even get the classical systems because there the connected automorphism group is trivial. Now we conjecture that this also holds with continuously struck out, and then we would also allow direct sums of isomorphic Jordan algebra systems. Haven't managed to prove it yet. So a little motivation now of these various properties. This continuous reversible transitivity appears in many characterizations of quantum state space. You're probably familiar with Hardy's. There's Müller-Massane's well-known paper with fairly weak assumptions that include this and the existence of entanglement. Hardy likes to justify the continuous part by the continuous nature of time. And there's important recent work of Galli and Massanes, maybe we'll hear about it, that assumes pure state transitivity. It might have a thermodynamic motivation. So von Neumann used it in his argument that the quantum von Neumann entropy should be the thermodynamic entropy. And then in this paper, we assumed it in order to derive the possibility of teleportation in suitable composites. There were some other assumptions there, which I won't go into. Okay, now what about the significance of homogeneity? Well, I first encountered it, and in fact first encountered the Kosher-Vinberg theorem in this book by Rudolf Haag. I think it's Rudolf Haag, Local Quantum Physics. It's only in the second edition, this discussion. And he said it's well motivated because you can prepare any state from any other, any interior state from any other. But every GPT system allows you to, at least formally, prepare any state, interior or not, via CP map. It's just this erasure map where you take everything to that state. So what's the special significance of assuming it can be done by automorphisms? So here's some kind of woolly-headed thoughts. Operations condition the probabilistic description of a state on an observation. And maybe these have a Bayesian or even Cubist flavor. Interior states rule out no measurement outcome. So you might argue that you never really should rule out a possibility absolutely, completely. So like the boundary of a finite dimensional cone, at least, is just a useful idealization where you assume some measurement probabilities are going to be zero. And the boundary states, in any case, you can approximate them arbitrarily well by full rank states. So maybe we're happy just thinking about full rank states and open cones. So operations that are order automorphisms are non-drastic. So if we're operating with these states that don't rule anything out, no outcome is ruled out after the operation as well. So if you like this idea of staying in the interior, then there's perhaps some motivation for order automorphisms. Again, this is, I think we're trying to make these thoughts a bit more precise and formalize them. Another thing about homogeneity is that it's equivalent to the affine isomorphism of all bases for the cone. So any way you slice the cone to make a normalized state space, you're essentially going to get the same theory. And that's because the dual is also homogeneous. It's not trivial to show, but Vinberg showed it. And therefore, well, and also any automorphism, the dual of that automorphism is an automorphism of the dual. So homogeneity is kind of telling you that non-drastic conditioning preserves the probabilistic structure of a system. So if you have this sort of cubist idea that the quantum formalism is a framework for thought, it really shouldn't change when you condition on some knowledge. And different people, in fact, have different knowledge. And are they going to be using drastically different convex sets to model the theory? Well, maybe, but it might be nice if they didn't. Okay. So I think now the time is up. Is that right? Yeah. Okay. So I'll just mention that in this paper we related homogeneity to steering, and also related it to unique purifiability. So there may be some interesting, I think there are some interesting reformulations of this result that related to purifiability and cast it in a little different light. Okay. I mentioned spectrality. Let me just say for strong symmetry and spectrality that if you think about a lot of these protocols for taking one quantum state to another quantum state in the presence of a bath, and you want to show that you can do it whenever the free energy doesn't increase, you end up with protocols where you often measure in the eigenbasis, and then you do various transformations separately on the eigenvectors. You want to be able to freely move to any other eigenbasis, and that's basically making use of spectrality and strong symmetry. So maybe, at least this underlies some important quantum thermodynamic protocols, and that might be another reason why it's nice. And I think I'll stop there then, and yeah.
Okay, we have one question there.
So an obvious question for me, I guess. Your assumptions are basically correct also in the infinite dimensional case. It's clear that asking for a characterization by the same sort of axioms in the infinite dimensional case is maybe a bit asking a bit too much at this time, but they're all true except perhaps that the interior is not the interior topologically.
Yeah, I mean,
it's the interior is that's in finite dimension. That's a nice way of saying the states that make nothing zero, but that is the statement that you have to use. But then it's also true, right?
So I don't want to say anything, I don't want to assert too much certainty about infinite dimensional results. But for example, I think that may be right. And yeah, I know that the topological interior is different according to various topologies, and sometimes it's empty. And there's also something called the algebraic interior that I've forgotten what it is that somebody defined. But so I'll mention that Alain Connes or Con, has an infinite dimensional analog of the Kosher-Vinberg theorem, but instead of this interior transitivity, so he used self-dual cones in a Hilbert space, self-dual according to the inner product. If it's complex, obviously it's the real part of the Hilbert space. But so there he used what he called facial homogeneity, which basically says if you take any two closed faces of the cone that don't intersect, you can, well, he said it in an infinitesimal form, and so it's a statement about the Lie algebra, but basically it says you can independently stretch and shrink them. It says a certain element defined in terms of the projectors onto these spaces lies in the Lie algebra. And that's, that's all certainly holds in fact, in finite dimension, that's equivalent to this interior homogeneity. Yeah, so maybe the reason he used that is that it avoids having to talk about the interior. Also, Belisard and Joachim have some results, though, where they do talk about, I believe, well, okay, I think maybe what one could say is they generalize Con's work to larger classes of of things than just starting with a Hilbert space, self-dual cone Hilbert space. They get to von Neumann algebras and C-star algebras. Yeah, but I think they do also use facial homogeneity. But yeah, I mean, it would be interesting for me at least to understand how this relates to interior and when it doesn't exist and what the different notions are.
Okay, so maybe we give priority to online questions because they are not here, no? So, yes.
Yeah. Can I ask that question?
Yeah, sure.
Okay. Hello, Howard.
Hi.
This is Alexa Greenbaum. So I would like to probe, you started the discussion about continuity, and I would like to probe in that direction a little more.
Mm-hmm.
You talked about this continuity of transformations between states and that assumption. There is also the very assumption that you are starting with a space, right, which is based on a field. And that field, you didn't say you suppose that it's a continuous field. All your drawings were in, supposing that this is some kind of a continuous field with probably an index 0 or something. So are these two things, how connected are they for you? And also, there's been a lot of debate, as you know, Nicolas Gisin, who is in the audience, I guess, there, and other people who said, well, we should get rid of all these reals or, really continuous number fields for the reasons of complexity. They lead us to non-empirical assumptions. Can you accommodate this kind of analysis in the GPT framework? What do you think about it?
I think one probably could. I'm not sure how important it is to try to do so, actually, and that may be because I'm not familiar with, all of the work that you mentioned. I mean, we're basically assuming it's the reals. It's an Archimedean ordered field. I think if you wanted to, you could do things with a non-Archimedean ordered field, and have a decision theory where there are, you can condition on things that have probability 0 at one level and whatever. But as far as discrete stuff. Again, I tend to think of the continuum is a nice approximation. I mean, even if you just believe that, all of our physics should be described in terms of statements that we put on a finitistic machine or in a book or something using a finite alphabet, I mean, it's still just often the best thing to do is to approximate it by a continuous or infinite dimensional setup. And I usually don't see any, I'm not really aware of any major problems that I think are coming out of that.
No, but you see, I think we saw that things like contextuality, like salient features of quantum theory, can be found in models with finite fields. So do we need all this machinery, which is so unempirical, in order to find the salient features of quantum theory?
I mean, I guess I think that, we're dealing with affine spaces over the real numbers and convex sets. And at least in finite dimension, that's sort of a pretty common language that most people understand. And to me, something like these observations about modal, like Ben Schumacher had some work about entanglement over finite fields and things. It's sort of less intuitive to me. So I guess that's my take on it. But I think I probably need to look more at some of these arguments. So we should, you should send me the references you think are the most important, and maybe I should have a read. Yeah. Okay, so thanks.
Okay, so do we get it? I mean, okay, one last. I mean, I will take online questions if you don't mind. Okay, so you can always talk to Howard, who is here. And okay, can you ask your question? So it's Professor, I didn't... okay, sorry. Who?
To me or what? Sorry. Am I supposed to ask a question?
Yes, please.
Oh, sorry, I wasn't.
No, it was my fault. Sorry, go ahead.
No, it's my fault. I'm not so familiar with these modern ways of communication. I mean, I have to say that I'm fascinated by the maturity of your field and by what you presented. It's certainly far away from what I know, but I simply want to express that I'm really impressed. If I can, I want to ask you a question which fascinates me for a long time, and which maybe you can comment or just give me your opinion, or if not, is also okay. It's the question of the number of mutually unbiased bases. I have been fascinated by this since I ever heard of it. You know, these famous papers by Ivanovich and by Wouters, that they exist for powers of primes and so on and so on. And for number 6, they seem not to exist.
Yes.
And you know, why do I find this mind-boggling? Because we apply mutually unbiased bases, for example, in communication schemes. You know, the complementarity of mutually unbiased bases is part of the security idea of these schemes. Now, why in the world should a number theoretic feature of the dimension of the Hilbert space, where a system is defined, have to do with the ways, with the number of independent ways how I can communicate, and particularly why should be the number 6 worse than the number 5? This is something I wonder for a long time, and you know, I don't know if anybody can give an answer or whatever.
So I actually remember when I was a postdoc with Herb Bernstein at Hampshire, and you came to visit, and I think I told you about mutually unbiased bases, and you were immediately fascinated. So this is fascinating to, again, meet up about mutually unbiased bases. So I think what I'd say about that is that although they don't exist in all dimensions, it's probable that very good approximations exist.
Oh yeah, sure.
Just as a typical, you know, I mean, if you randomly choose a bunch of bases, they would probably be close to mutually unbiased. And then if you did some work, you could probably get ones that were even closer to mutually unbiased. But yet you couldn't exactly get there. But if if these things were actually efficient to use, these approximately mutually unbiased bases, you could probably do a pretty good cryptographic protocol of the same sort as you would do in dimension that actually had the mutually unbiased, using the approximately mutually unbiased. So it's just sort of a freak of combinatorics that you can do this protocol perfectly in some dimensions and not others. So that's maybe not a very deeply satisfying answer, but I do think that, you know, looking at typical structures, even if they're not precisely the most combinatorially beautiful ones, is often a good approach in quantum information theory. And then there's always the question of, you know, if you have a nice combinatoric description, often that comes with an efficient way of preparing it, whereas if you're just making arguments about random bases, that does not come with an efficient way of preparing it. So that's a problem. But yeah, that's a nice question.
Thank you.
Thank you.
So I think we move on now, because we thank Howard again.
Thank you.